So we were discussing that thermal sensation is really relative. That's why if you want for each region, we develop like a chart with comfortable zones. And we do some testing on people in a certain region to come up with a recommendation for an acceptable zone. And as we discussed, depending on the climate we are familiar with, these zones can vary. Okay, so once we define a comfort zone, when we design the ventilation system, of course, we should try to be within this zone. So we have some recommendations on the level of humidity and the level of temperatures that are allowed. So we should stick to this zone to ensure thermal comfort. Now, concerning the environmental impact, whenever we want to study the environmental impact of when we design a passive building, we should look first at the inlet energy and material flows. So what are the materials that are used, let's say, to build our system? Do we have materials that are harmful to the environment? Do you have possibilities that with time we have deterioration, we have these materials will have a bad effect on the environment, etc. So we should also study the outlet energy and material flow. So the waste production, what are the pollution effect on the environment? So whenever we do environmental impact on a project, we should study it during the whole lifetime. And also here we have regulations, let's say on the maximum generation of CO2 per year, on the if you want the effect of material, what are the materials that can be risky for the environment that we should not use in construction, etc. At any stage of the building life, we should follow up with materials and equipment fabrication, the construction, the operations, the renovation, destruction, and at the end, possible recycling of some materials. We have several impact categories that we can also work on. For whenever we talk about energy resources reduction, we should try to do a passive and go to positive design to reduce relying on oil, gas, coal, and we should reduce the greenhouse gas emissions by reduction of, we reduce global warming effect by reducing greenhouse gases emissions. Also, another concern is acidification of water. So this is very important to study to avoid, if you want, the effect of acid rains on the environment. We should make sure that we don't have any risk for biodiversity reduction whenever we relate it to the building materials that we are using, or let's say if you are selecting the land, you should not, let's say, remove a lot of trees, etc. On the other hand, the economical impact is also very important. So the cost is one of the major importance of an energy building project. And this is why energy economics is a very important field, because for any project related to energy, one of the main concerns will be to perform an economical analysis and to make sure that it's an economically viable project to encourage people to invest in it. So the cost is of major importance, and it should include the study of the land cost, the design cost, the construction cost, the operation cost, including energy bill, water bill, maintenance, waste treatment cost. In next chapters, we'll develop a lot of economical techniques that can help us perform the economical analysis for an energy project. A better performance may reduce some operation costs, but also may imply investment surcharge compared to standard building. A global economic evaluation then will be needed to evaluating this aspect. The life cycle cost method is a method that will consider the overall surcharge that can be balanced by the overall environmental benefits of the eco design. So in this course, we'll develop a lot of economical tools allowing us to study the economical impact of a certain energy project. Now, as we discussed, Also, energy efficiency is one of the main parameters to consider in the design. We should try to increase the energy efficiency, reduce the energy consumption to meet a requirement of passive buildings. So energy consumption will have impacts on both environmental and operating costs, and it is expressed for a defined time period. So in general, the unit will be in kilowatt hour per meter square per year. Using, if you want, specific values is very important, because you know that if you have a large building, of course the consumption will be larger. So always you should scale, you should divide per meter square per year in order to be able to compare several projects. Now, concerning heating and cooling needs, they are expressed per unit area, also square meter of heated area. And the accurate definition will depend on the regulations and convention. You know that depending on the country, you have different regulations for heating and cooling needs. Because as we discussed now, in different countries, you have different climates, you have different thermal sensation, different need. You know that, let's say, peoples of Africa tends to support a lot large temperatures, while let's say people in Canada can be comfortable even with small temperatures because they are used to these temperatures. So the heating and cooling needs will vary a lot from region to regions. That's why regulations also and conventions imposed will be different. And we will always go to standards. Let's say you have, for example, ASHRAE standards that study different regions and give recommendations of heating and cooling needs for different regions. So always here we should abide with regulation. We should go to standards, go to energy policies and regulations to have an idea what are the goals that we should achieve in our design. The final consumption will depend, of course, on the efficiency of the heating device. That's why working on increased efficiency of devices will lead to reduction of energy consumption. A very basic method, if you want to study energy flows, is to represent it by the following diagram, which is like a small flow chart that will help you if you want to study what are the energy inputs, what are the energy outputs, what are the losses. So for example, if we take a building equipped with a wood condensing boiler and thermal solar panels, so we are using two sources of heat, okay? Wood, which is non-renewable, and the other source is solar panels using renewable energy. So as you can see, first, you have here the total energy that, if you want, you are using. You are importing, let's say, 9,574 units of energy. Okay, from this total number, you are using 4,161 for electricity. You are using from solar heating 3,227, and from wood you are using 5,413. So you have several sources to supply the needs: electricity, solar heat, and wood. Now, you can, in this diagram, you should determine what are possible losses. Of course, in wood, you will have the major losses because in combustion, you have a lot of waste energy because you know that you can have a humidity level for the wood. So you will lose energy to evaporate water. Plus, you have exhaust gases that will lead to some losses. So let's say you can extract usable heat of 4,060, while for solar heat, you will use it, let's say, completely, and for electricity also. So you can determine the useful heat for, let's say, heating and domestic hot water, and electricity will be used for electricity, cooking, ventilation, and light. So this diagram will help you to know what are your inputs, what are your outputs, what are your losses, to study the energy efficiency of your system. Now we have some basic rules to draw such diagrams. So once you know these rules, you can understand easily the different arrows. So we should do first identification of each flow with numerical values. So what are the main sources of energy, how we can decompose them, what are the losses, what are the useful heat. And if you want, we use, let's say, proportionality in scale. Okay, and we consider that you use a certain scale, let's say. So this represents a total value of 9,574. So you should try to, if you want to have middle proportions, this percentage, let's say if you measure it, it should be, let's say maybe 40%. It seems 40% of 9,574, etc. So you should have like you should verify a certain scale so that you can just from looking at the figure have an idea of the percentages. So the arrow's width should be proportional to the flow of energy. There is no change in the arrow width without branching or merging, because you know that energy is conserved, but just it can change of form. And in general, inlet flows will come from left, and losses. So here you have inlet flows coming from left direction. Okay. As you can see here, the solar heat is not accounted in import because it's a renewable energy. Whenever you are calculating the import, you calculate energy, non-renewable energy, as electrical energy that can be from fossil fuels, wood energy that is from combustion. Okay, so you can see that 9,574 is the summation of the energy from wood and the energy from electricity, which are non-renewable resources. So we don't consider solar heat as import because we have it for free. Okay, and we add it here as a renewable resource, and this will explain why we have here a larger, if you want, length compared to this one, because this is only for the total scale, if you want, lengths for non-renewable energies. However, here it's summation of renewable and non-renewable. Now, when we use wood, we expect a certain percentage of losses. So as we mentioned, all inlets will come from left. Okay, losses will go upward. So here we have losses due to combustion. Now, for useful outlets, that will be directed to the right. So here are the useful outlets. Okay, and we can see here that let's say combustion energy from wood and the solar heat can be used, for example, for heating purposes, plus domestic hot water needs, while electricity can be used for several purposes as lighting, any device needing electricity, cooking, ventilation, etc. So this diagram can be, if you want, a good presentation and a simple presentation to see what is the energy you need to import, what is the useful part. You can try to reduce the losses as much as possible. You can try to rely more to increase the percentage of renewable energy if possible, etc. So here, for example, we are applying this diagram on another application. Let's say you have an engine block that you are using. We know that, let's say, we have the total energy will be divided into, whenever you have combustion, you have a part that is lost by thermal energy, okay, released at the engine block. Let's say it's 10% of the total energy. You have also hot gases, hot exhaust gases that will leave your system. So you will have a certain part of waste energy. Look, this is really a high percentage. Hot exhaust gases can transport up to 40% of your total energy. So from here, the importance of using heat recovery. When we talk about heat recovery system, it means that we can use waste heat source in order to give heat to another, let's say, power plant or another system requiring heat. So let's say you can, for example, direct exhaust gases, let's say, toward a heat exchanger to heat, let's say, a refrigerant that can be used for domestic hot water, or for, let's say, heating, let's say, any giving heat to any power plant requiring heat to operate. So this is called heat recovery, because you are using waste heat in a useful form. And this can really enhance a lot your performance. Why? Because imagine you were able to recover 30% of the heat from exhaust gases. Then you will increase your efficiency from just 50%, which is the useful work, it will become 80% because your total efficiency now will be the useful work and the useful heat you can extract from exhaust gases. So heat recovery systems can increase in a large extent the performance and energy efficiency of a system. And this will be one of the major interests of passive building strategies. So here also we can use some diagrams to illustrate, if you want, how energy is converted from the primary stage to the end stage when it is used. So of course, at the first level, we have the extraction and production of primary energy. Then this energy should be first transported to places where needed. So of course, we'll have losses during the transportation stage. After, of course, also because of distribution, while you distribute energy, you have losses. When you transform it from one form to another, you also have losses. And in the final stage, okay, when you use it for your energy need, you also have losses. So you have a lot of sources of losses of energy. That's why whenever you do the design, you should try to minimize all sources of losses. So you should think about, let's say, the transport of energy. That's why when you start with a project, using selection of the land is very important. You should select a place that let's say is close to transport stations of energy, to not have large distances and a lot of energy losses. You should make sure that you are in a place where energy is distributed in an efficient way. You should use devices that have high efficiency of transformation of energy from one form to the other to reduce losses. And when you supply this energy, you should make sure that, for example, let's say you supply water, you should use water in an efficient way. You can implement systems as sensors, as we discussed before, to reduce waste of these energy resources. So primary energy is, as we discussed, for a given energy flow, it corresponds to the amount of raw energy extracted from the environment, which is needed to lead to the required energy flow. So if you want, it can be, let's say, in an example here of buildings, it is the primary materials that you can use. So let's say to construct your building, you need materials. So in their initial forms, they will constitute a primary energy. Then you can, these materials, you need to operate them, you need to do some manufacturing, you need to go through different stages to make them used for construction purposes. And any type of energy can be categorized in several ways. Let's say the fossil fuels in the primary stage, the elements that constitute fossil fuels, etc. After this, we should transport fossil fuels. We should do combustion. When we do combustion, we have losses before being able to, let's say, extract some heat, and then the heat will be transformed into electricity by an appropriate system, etc. So all of these stages will lead to losses, and these losses should be minimized in all stages as much as possible. Now, in the final energy, we have actual energy content of any energy flow used in the building. Now, the useful energy corresponds to the energy amount required to supply the service, including thermal comfort, visual comfort, electronic device powering, etc. Now, whenever we want to have, when we want to study a building, of course, we should know all constituents of the building in order to optimize its design. So first, one of the major parts is the envelope. The envelope, which can be divided into walls, openings like doors and windows, the roof, the slabs, the foundations. We should also consider the outer environment. What are the outdoor conditions? Let's say, what is the temperature of air, the relative humidity of air? What are the conditions of the sunlight? how much rain we have, what is the state of ground. And for example, we want to use, let's say, geothermal energy. We should study the ground, what are the materials, etc. Inside the envelope, we should look at the load-bearing walls and partitions, the coatings, the furniture, the equipment, the plumbing system used, the number of people, because we want to assess what are the loads, the lighting loads, the heating and cooling loads, etc. And of course, whenever we want to study the envelope, we should know, we should understand the interaction between the outer environment and the inner environment. So how energy is transferred between these two zones? What are the basic heat transfer processes? We know that the basic heat transfer processes are conduction, convection, and radiation. For example, if we want to study an energy, a building on the energy level, we should know heat is transferred through which modes to the internal environment. If you want to model in ANSYS, let's say a heating ventilation system, we should know the heat flux coming from walls. So we need to know what, to compute this heat flux, we should know the modes of heat transfer. So here we'll discuss in a brief the different modes of heat transfer: conduction, convection, radiation. What is energy storage? Sometimes inside your home, you can put material of high capacity that can, let's say, store energy during the day where you have excess of heat, and release it during the night where you need it to heat your space. So for example, energy storage will be very efficient to use in Bekaa region in Lebanon, because you know that in this zone we have very large temperature difference between day and night, and therefore implementing such systems in the building will reduce a lot if you want fluctuations of temperature inside the building, because in the day you have a lot of sun, you will have penetration of heat fluxes towards your room, which will lead to heating of air. In case you don't have, let's say, for example, a materials that can store this heat, this will lead to overheating of air inside your room. However, if you have, let's say, an energy storage system implemented, let's say underfloor, it will absorb this heat during the day. And during the night, when you have a high decrease in temperature inside the space, the heat will be released back by the energy storage medium, and then you will ensure, instead of having large variation in temperature between day and night, you will dampen these by differences. Okay. Now, whenever we study the energy performance, we should know the different fluxes of energy, how energy is transferred between the indoor and the outdoor space. So we can talk about, for example, the solar gain from the outer environment. We should know the internal gains. That's why we need to have information about the number of people, the equipment we are using, etc. We should know if we have some heat storage elements inside the building, to know if we have overheating, if the heat storage will be able to act then instead of having overheating inside the space. We should know what is the heat exchange through the wall, so we can study heat exchange by conduction within the envelope, because we'll see together that mainly in a solid, the main mode of heat transfer will be by conduction, that we'll discuss in a while. And whenever you have at the inner and outer sides, the main mode can be convection, because you have a fluid moving over a surface. Plus also, because of the difference in temperature between the surrounding and your surfaces, you can have heat exchange by radiation. Okay, so we'll go deep into some equations of these processes and how to implement, let's say, them in simulations next time. Okay, any question on this? So of course, whenever you determine these different fluxes, you can write the energy balance for your system. So you know that energy cannot be created. Energy can be transformed from one form to the other. So in case you are considering your internal space, Okay, you can say that the energy stored in my space is equal to the summation of fluxes coming in minus summation of fluxes getting out plus what is generated inside my space. Okay, and I will try to keep comfortable condition inside. That's why I need to avoid storage. So let's say during summer, I don't want to store energy in air because this will lead to increase of its temperature. I can store it in, let's say, in phase change material or in a medium of high capacity because it will release it back to air when needed. Okay, but I don't want to store it in air. So I don't want to increase the temperature of air. I tend to go to steady conditions, and to ensure these steady conditions of acceptable temperatures, I should study, let's say, what is the ventilation required for my space, okay, in order to overcome the internal generation, in addition to the inlet fluxes that are and outlet fluxes that are exchanged with my external environment. Okay. So this is the material we'll tackle for today. Any question before we stop? Okay, so hopefully next time we can start with learning about ANSYS Fluent, how to do energy modeling inside a building. Okay, see you next time. Bye.
Thank you.